When we talk about vectors, since we're talking about direction and measurement, when we're measuring two different things, it is used in a ton of physics problems, right? Because when you're talking about force, you're going to see trigonometry come to play. When you talk about bearing, like how something is traveling, you're going to see this trig come into play. Because they will often tell you, well, it's going this fast for this long, or it's traveled this many miles in this direction. And so they are telling you two different things. They are telling you which way it's going and how fast it's going, or which way it's going and how long it has traveled, or something like that. And so that is where we start getting into types of word problems, especially when you have two different things that are emphasizing the same object. So you'll have two different entities that are affecting something, a speed of an airplane and the speed of the wind. Those are two factors on what's going on. And so you'll also often see these vector problems in types like that. So we're going to start then with just resolving components, introducing the trig piece of it, and then we're going to apply it to some word problems. So if you go to page 290 in your books, we are going to start with the term resolving a vector. So right above example 6, you'll see a vector expressed in terms of its magnitude. And remember, the magnitude looks like an absolute value. It can be a lowercase letter to tell you which vector they're specifically talking about. Its directed angle, theta, from the positive x-axis can be resolved into a horizontal and vertical components. Okay, so think about what's happening. If you see that picture in the answer there, if you are talking about something from standard position, meaning from the x-axis around counterclockwise, then the reason trig works is it's going to create a right triangle, all right? And so when they give us a coordinate plane here, and then they tell us where the angle is, in this case, they put it over here, all right? This is going to drop you off somewhere, and no matter where it drops you, you can create a right triangle, all right? And so if you look at horizontal and vertical movements, then you should be able to look at sine and cosine. The sine of the angle compared to the opposite, the sine of the angle, or the cosine of the angle compared to the adjacent. And so that's where we get this right here from. If you take how far it's traveled on that vector, so the magnitude of this vector, how long this guy is, and you multiply it by the cosine, you are going to get how far it's traveled horizontally, okay? And the reason that's the case is because it's going to be adjacent over hypotenuse, this being the hypotenuse. And so if I were to do the cosine of this guy, but I'm solving for the horizontal movement, you would say, well, I have x over h, adjacent over hypotenuse, that equals my cosine. Well, what if I'm solving then for the adjacent or the horizontal movement? Well, I would multiply by that hypotenuse. In this case, the hypotenuse is the magnitude. So that is where we get the magnitude times cosine giving us our horizontal movement, all right? Or a horizontal component. Same place as how we get this one. The magnitude, or in this case, the hypotenuse times the sine is going to give you the opposite side because of the whole SOHCAHTOA. That's how we're going to get these two. And so if you remember where it came from, it may help you remember how you're going to get the next piece of it. So when you are trying to resolve it into a horizontal and a vertical component, you are going to use your trig to do that. Cosine being the horizontal, right? Your x, left and right. Sine being your vertical, your y, up and down. All right? So that's what we're going to do with this word problem here. So let's look at this first one. It says, state the component form of a vector representing the velocity of a plane flying 30 degrees west of north at 40 knots. Then express the vector as a linear combination. All right? The first thing you have to remember is kind of your bearing information. A couple things you need to know. When they say west, they are always typically talking west of north, even though they were kind enough to tell us that. They're usually starting at true north, and they will tell you west or east or however it's moving. If it says a true bearing actually starts at true north and goes clockwise. versus standard. Standard starts at the x-axis and goes counterclockwise. That's what we're used to with unit circles. So standard starts at the x-axis, goes counterclockwise. True bearings start north and go clockwise, all right? But if it tells you a direction, then you're just going to use your north, south, east, and west, which hopefully we all know those, all right? And then you're going to do what it says. So it was traveling 30 degrees west of north. That tells us that this is where we are. This guy right here is our 30 degrees, okay? That's what that is telling us. That is our 30 degrees, all right? So then we have to figure out, well, what is the standard movement then? If I moved 30 degrees right here, how far have I moved standard? Well, I've moved 120 degrees, right? So from the standard position here, I've moved 120 degrees. 120 degrees. From that, I am going to use my sine and cosine from standard position, okay? So when I look at standard position, 400 knots is actually telling me this guy right here, 400. So when it tells you how far it's traveled, that is your hypotenuse. That is your magnitude when it tells you how far it's traveled. They want us to give it in vector form with your x and y. And so that's what we're going to do. We're going to put it in vector form with x and y. We're going to use our magnitude, which was 400. And we're going to multiply by the cosine of our standard angle, 120 degrees, to find our x value of that vector. And then we're going to do the same thing, but use sine for our y value. All right? And so then you're going to plug that in. You will get approximately, which this one is a nice one. It's one that we should know, our 60 degrees in the second quadrant. So my cosine is -1/2. My sine is square root of 3/2. Or you can put it in your calculator, right? As long as you're in degrees. If you put this in your calculator, you will get approximately 200. Well, exactly 200. It is negative. Why is it negative? Well, I'm in the second quadrant, right? And then it will also give me a decimal because square root of 3/2. So 346.4 for my y value. Now, if you look at that visually you should look at this and say, okay, I definitely should have a negative x and a positive y, right? And so if you are able to sketch a picture of these, it gives you an idea if you're on the right track when you do this. It also said, once we find it, express it as a linear combination in unit vectors. Remember, unit vectors is with the I and the j. So you're pretty much there, -200 I plus 346.4 j. That is the approximate combination for this vector. An object's velocity represents its speed and direction. So when you talk about speed, that has no direction, okay? So if you tell somebody you're going 50 miles an hour, that has no direction. You are not telling me anything about where you're going. It's just how fast you're going, okay? But when you say velocity, velocity adds another element that includes direction, okay? So like when you hear an initial velocity for like something being thrown up in the air, the fact that you know it's being thrown up at a specific speed, it tells you have velocity, okay? Because then you have gravity, which has a negative, right? So gravity has pull and it's pulling down. And so you're going to have these two things come into play. And so anytime you hear the term velocity, it is a vector that represents both speed and direction. It is a frame of reference. So the next line is very important. It is, the object is relative to its frame of reference. Like it says, a blimp's speed is relative to the air around it, maybe 20 miles per hour. but the ground speed of that blimp may be different relative to the Earth. So it gives the example. If it's flying into a 15 mile an hour headwind, is only 20 miles per hour that it's traveling. So then it's overall, how you look at it from the ground is only 5 miles an hour because it's got something going against it, right? And so anytime you have velocity of something moving through something, whether it's air or water, we've done this with boats, right? And airplanes. If you think back to like Algebra 1, Algebra 2 word problems, we had to consider the speed of the wind and the speed of the airplane, right? The same is true here. The resulting ground velocity of a vessel that is moving in something has to take into consideration what it is moving through and the velocity of that, okay? So that's how this next word problem is going to be set up. Leanne wants to swim straight across a 300 meter, not mile, wow, that would be long, a 300 meter wide river flowing at 0.4 meters per second. At what angle upstream to the nearest degree should she head if she can swim 1.5 meters per second in still water? How long will it take her to cross the river? Okay, so we're going to draw a picture of this. And I typically always draw these on a coordinate plane, just because that's going to give you an idea of your angle. All right, so we have this coordinate plane. If they're telling us that she has to swim upstream to go against the current, we're going to assume the current is moving what direction? Downstream, right? So we're going to just say, well, we're going to assume that the current is moving downstream if they say that she has to travel upstream. And we know how fast it is traveling. It is traveling at 0.4 meters per second. So that's this guy right here. All right. She's going to be traveling upstream, not directly upstream, but across the river, right? So she's going to be traveling from her starting point across the river. Now, why am I drawing it at an angle? They said she wants to go straight across. She has to fight the current. If you've ever been in a boat, you understand that it doesn't matter what happens in still water. If you are moving in moving water, it's going to change the boat, right? If you have ever had to pull a boat up onto a boat ramp, right, you'll understand this completely, right? Because you're perfectly straight and the water's doing this. So what do you have to do? You have to compensate. And that's what they're wanting to know. How is she going to have to compensate? We know how fast she can travel in still water. So that is going to be how fast she is traveling on her own accord. So this line that I just drew is going to be the 1.5 because that's all she can give us, right? That's what we know she can do. So now we have to figure out then, what does this have to be so that she ends up doing this? Okay? So we need to know the angle at which she needs to do that so she ends up with her force and the force of the water pushing down on her to end up going straight across. Okay? So now we're trying to find at what angle does she need to go across? Well, we have set up a perfectly good little thing. If I am trying to solve for this angle, I have the opposite side and I have the hypotenuse side, right? Even if I didn't know that, okay, I do know that I have the vertical movement there, which is going to be my sine, okay? I already know I have this piece of it, so I know I have the sine value. So if I'm trying to solve for an angle, what am I going to use in my calculator? The inverse. So in my calculator, I'm going to say the inverse sine of the opposite divided by the hypotenuse. And you should get, rounded to the nearest degree here, approximately 15 degrees. All right, approximately 15 degrees. They also want to know how long it will take her. All right, so a couple things here. If we want to know how long it's going to take her, and everything else we've done has been in speed, right, and velocity. We have done velocity here, then what do you think we're solving for if we do this? Velocity, okay? So we can use Pythagorean theorem to solve for velocity, but that's not actually what they're asking for, all right? So if they ask how fast would she actually be traveling in the moving water, then this would be the end of our problem. But we need to know how fast she's traveling, and then we need to multiply it by how far she's traveling to figure out how long it will take her, okay? So the first thing we have to do is figure out how fast she's actually traveling, considering the fact that the water is going against her. We're going to use basic Pythagorean theorem to do this. All right, so Pythagorean theorem is just a squared, which we do not know, plus b squared, which is the other leg, equals c squared. All right? So when we do that, we're going to see that she's traveling approximately 1.45 meters per second, okay? They said, how long will it take her? Well, how far is she going across? 300 meters. She's going 300 meters at 1.45 meters per second. How do we find out? Just divide. All right, and it should take her approximately 207.5 seconds. I would actually probably convert that to minutes because that seems like a weird way, and that seems really quick, but whatever. Divide by 60, you'll get how many minutes she's traveling, right? Right? And so, 3.6 is 5? Right, she's flying, right? So, unless 300 meters is not as far as it sounds, but if someone threw me in the water and told me to swim, it would seem a long way to go. So the first thing they ask here is how far. How far did he travel? That's going to be the length of the sky. That is straight up Pythagorean theorem. Okay? Yep. How far did he travel? Okay? Because they gave you how far. So that means all sides of your triangle are going to answer that question. Okay? You'll never have two different, think of it as units. You wouldn't have feet and yards and then just solve, right? So if this is how far and this is how far, this is how far, all right? So they want to know how far he traveled from his original. Well, if he started here and went down and over, how far is going to be the hypotenuse? So that's straight up Pythagorean theorem. 80 squared plus 50 squared, take the square root, you get 94.3. His bearing, that's where you want to slide it up here, because bearing is always from their point of view. He's not magically sitting in the third quadrant of the world, okay? That's not how this works. So when you're answering the question of bearing, just slide him up here. It is the same exact triangle. Use inverse tangent. You have solved for this piece of it. They want bearing. If they said standard position, which they rarely do with direction, then you would give standard position. If they give it to you in like northeast west, you could say so many degrees, but then you would say east of north, which is the bearing anyway, okay? Because you're always referencing back to north when you're talking about bearings. The other thing you can have is force. This one is not as intuitive, I don't think, when you start to draw this one. A 10-pound sign hangs motionless from two ropes, each at an angle of 60 degrees above the horizon. Above the horizon. So by the way, when they say something like that, they mean something like that. Find the tension in each rope. All right. So the 10 pounds is the tension that they told you the sign was putting on itself. Okay. That's what they're telling you there. So they're trying to find the tension of the two ropes. And so you want to draw this again on a type of coordinate plane, and you're going to do, some sliding around the coordinate plane as well is what you're going to do. So the first thing you want to do is kind of figure out what's going on. So I'm going to draw this right here. And I am going to draw what's happening with my sign. Well, my sign is pulling down on it at 10 pounds, right? That's what we know. From the horizon, the two ropes are pulling up. So each rope is pulling up. That looks more like 45. So we'll do it something like that. Up. We'll say those are about 60 sketched, right? Okay, so that's what's happening. All right. There's a couple ways to do this, but you can actually slide this around. So you can slide, do like a tail to tip type drawing. Meaning you have, oh, that's not pretty. You have something going on right here. All right, we're going to say, we're going to leave this first guy, the original one, right here. So this is going to be 60 degrees. This direction, which means it's going to be, if this is my 90, and that's 60 degrees down here, then this guy's going to be 30, by the way. So that's him. That's this one. I'm going to slide this guy to up, all the way up to the top here. That's what I'm going to do. I'm going to slide him all the way up here. So now this guy is going to be up here. Okay? All right, he's going to be right there. If I have, and so he's also going to have this 30 degree. If I have 30 and 30, how do I know what this guy is? It's actually going to be those two added together, right? It's going to be 120. Everybody agree with that? That this guy's 120. He's my 260s that were left over on my 30, 60, 90, and then they got put together. So this is 120. I'm going to slide this piece of it up. So I'm going to put him here. He's going this direction on the 10. Okay? All right, so we have 120 over 10. 30, 30, what type of triangle is this? Let's pull back from geometry. It's isosceles. I know that because my two base angles are the same, which means those two ropes are pulling at the same, which makes sense, or we'd have a lopsided sign, okay? But those two ropes are going to be the same tension that's happening there. All right, so I really just have to solve for one, and I'm going to answer my question. Now, we're going to pull from last chapter, all right, and from last year when we did law of sines and law of cosines, okay? This is not a right triangle. I cannot use right angle trigonometry, all right? But I can use the side length over the sine of my angle should equal the side length over the sine of the opposite angle there, which should equal the side length over the sine of the opposite angle there. Law of sines, side over sine, all right? Any triangle, the ratio between the opposite side and the sine of the angle will always equal, okay? So I can say I have 10, so 10 over the sine of 120 degrees should equal the tension of one of those ropes over the sine of 30 degrees. How do I solve for that x? Multiply both sides by sine of 30. So 10 times the sine of 30 degrees divided by the sine of 120 degrees should equal what? What do you get?
Would you
5.8 pounds of force.